circle theorem that you need to know on the ACT is called central angles. And if you already know this one, it's super easy. But if you don't, let's just quickly review it. A central angle is an angle whose vertex sits at the center of the circle. Its two sides are radii, lines running from the center out to the edge of the circle. And the rule could not be simpler. A central angle is equal to the arc it cuts off, its intercepted arc. If the central angle is 110 degrees, the arc it opens up to is also 110 degrees, same exact number. About inscribed angles, these are not as common to see as central angles, but let's learn what they are. The vertex of the angle in an inscribed angle sits on the circle itself, right on the edge, with its two sides being chords that reach across to the arc that it intercepts. And here's the one rule that unlocks all inscribed angle questions on the ACT. An inscribed angle is exactly half of its intercepted arc. Half size reading. So if the arc is 130 degrees, the inscribed angle looking at it is 65 degrees, half of 130. Now let's talk about sectors and arc lengths. These are more common than inscribed angle questions on the ACT. And if you never learned how to calculate these questions, they are confusing, but really you just have to know the area of the circle, the circumference of the circle, depending on whether you're looking for the sector or the arc length, and then the ratio of the circle that is taken up by that sector. A sector, a pizza slice, if you will, of a circle with a central angle of n degrees. That slice is n over 360 of the entire circle. To get its area, we take that fraction times the full area of the circle. The full area of the circle is pi r squared. So the sector area is n over 360, because there are 360 degrees in a circle, times pi r squared. Same logic for the arc length, but we're talking about the circumference of the circle. It is the same fraction, n over 360, about the length around the circle, not the area of the circle. So it's n over 360 times the circumference, which is 2 pi r. So arc length is n over 360 times 2 pi r. Now let's say the radius is 10 and the sector's central angle is 72 degrees. The fraction is 72 over 360, which actually simplifies to 1/5. The area is pi times r squared, 10 squared, so 100 pi. The area of the sector is 1/5 times 100 pi, which is 20 pi. And if they were asking for the arc length, then it would be 2 pi r, so 20 pi times 1/5, which would be 4 pi. ACT most commonly sets for these area, sector, and arc length questions are typically based on deciding whether or not you calculate the length of a curved line, the arc length, or the area of the sector. So if you choose to calculate the area of a sector when you're supposed to find the length of an arc, it will almost certainly be an answer choice. The area will be an answer choice even if you're supposed to calculate the arc length. They want to trap you into doing the wrong calculation. So always make sure that you calculate the correct number. If you're looking for the area, use pi r squared and the central angle. If you're looking for the arc length, you use 2 pi r times the central angle. All right, now let's talk about tangent lines. So this is the final core idea, the final one that you are likely to see on the ACT. And it turns circle problems into triangle problems, which sounds weird, but this is what it means. A tangent line is a line that just barely touches the circle at a single point, just kissing the edge of the circle without crossing into the circle. Radius drawn to the point of tangency, and the point of tangency, again, it's a fancy word for the exact spot where the tangent touches the circle. So the radius drawn to the point of tangency is perpendicular to the tangent line. It meets at a perfect 90-degree angle. Tangent line, perpendicular, and the radius. Whenever you see a tangent, immediately draw the radius to the touch point and stamp a right angle there. Why do you care? Because the right angle means the Pythagorean theorem is going to be available for this triangle problem we are most likely going to have to solve. Line hands you a right triangle so you can solve the problem. So here's a real question. A line is tangent to a circle at point T. From external point P, the distance PT is 12. The distance OP from the center O to P is 13. What is the length of the radius OT? The choices are A1, B5, C12, and D25. Draw our right triangle with the radius going to the point of tangency. Then we have a right triangle with one leg length of 12 and the hypotenuse of 13. Now, we use the Pythagorean theorem, and we can have 12 squared plus OT squared equals 13 squared. So that's 144 plus OT squared equals 169. Subtract 144 from both sides, we get OT squared is equal to 25. Take the square root of both sides, and we get OT equals 5. So the radius of this circle, OT, is 5. That's answer choice B. Review. A central angle equals its arc measure. An inscribed angle is half its arc. A sector is a fraction of the whole, n over 360. And remember, sectors mean area that uses pi r squared. Arc length is looking for the length of the outside curved arc. So we are using the circumference, n over 360 times the circumference, 2 pi r. Make sure you know whether you're finding the area of a sector or the length of an arc. Area uses pi r squared, arc length uses 2 pi r. A tangent is perpendicular to the radius at the point of tangency. If you draw that radius and stamp the right angle, you will find that you can get a right triangle and use the Pythagorean theorem.